Hello, hello. It is Mrs. Edwards and we are back. It is time to do math and I love it. Today we get to solve some logarithmic equations and I'm calling this video part 1 because we're going to start off with some kind of basic solving of logarithms. We'll build up just a little bit, but then eventually we will do one more video of solving logarithmic equations where we tackle some even more challenging equations. But really, all of them come down to the same strategy. You know, I don't know if you're into some tactical battle games, or because maybe you have tried logarithms in the past and felt like you were doing battle with them, had a difficult time, but that's just because you probably did not have a solid strategy. In 2021, just saying, there are a couple of fun games that are coming out. We've got Warhammer Age of Sigmar, and then there's also Ages of Empire 4 and the King's Bounty 2. It's been 7 years actually since they have updated that game. It's going to be more tactical. So we're going to really approach solving logarithms like these games. We're going to isolate the enemy. We're calling the logarithm the enemy. We're going to get your enemy alone. So get the log alone. And then we're going to go to higher ground. In other words, we're going to go exponential and battle on. All right, so we're going to put that in action. But before we get the logarithm alone, go exponential and battle on, let's just quickly review how you could get a logarithm alone. You're simply going to be in these first kind of easier ones, you'll undo the order of operations until you get the logarithm by itself. Okay, so let's say I have a single logarithm by itself. Then step 2 is to go exponential, meaning that we change from log form to exponential form. Okay, so this is just a quick reminder of what log form looks like to exponential form. Those of you who have watched my video about changing from log form to exponential form, this is just a quick reminder that that beaver is tunneling under, coming up on the other side, pushing that y up. So we're going to have the base to the y, and because the beaver has tunneled under, the logarithm ends up falling in that tunnel, and we don't have that log anymore. Okay, but main takeaway, okay, a little bit of a red herring there. Main takeaway is when you're solving equations with logarithms, number 1, get the logarithm alone, because you're not going to be able to get x by itself instantly. You want to start by getting the logarithm alone, and then after you get the log alone, you're going to change to exponential form and then keep on solving. And you will be able to get x by itself, last man standing. All right, let's put that in action. Here we have our first example, log base 2 of x equals 3. We start with the question, is the logarithm alone? And in this case, it's a very basic equation, and yes, the logarithm is alone. So the next thing we want to do is go exponential. In other words, we're going to go for higher ground. That 2 tunnels under and comes up underneath the 3, pushing that 3 up. So we have 2 to the power of 3. The log falls in the tunnel, and so x is over there on the left by itself. X equals 2 to the 3rd power. We just went from log form to exponential form. A little simplifying, and boom, there's our answer, 8. X equals 8. We have got an x by itself, last man standing. All right, here we go. Let's do another one. We have a little bit more complicated one, but let's keep in mind when we want to solve, step 1, get your enemy alone. Get the logarithm alone. So is this logarithm alone? And no, we do not have one log by itself. So next, we want to undo the order of operations to get that logarithm alone. It's kind of that process where we can't just go after getting the x by itself right away. We've got to get the log by itself, and then we can get the x by itself. So let's undo the order of operations. I'm going to highlight what we've got going on there. So let's get rid of addition and subtraction. So I subtract over 4, and that's what we've got. Okay, next, get rid of multiplication and division. So I'm going to divide both sides by 3. Okay, and now is the logarithm alone? And the answer, of course, is yes. The logarithm is by itself. Right in front of ln, we have one natural log of something. Okay, now that we have our logarithm alone, we're going to go exponential. All right, so we're going to take that base number that we don't see, right, natural log of base e. E tunnels under, comes up under the other side, under the 2. So that right side is going to be e to the power of 2. The natural log there goes away. So we've gone from log form to exponential form, and then we just keep on battling. In other words, we're just going to solve now for x. So quick reminder just from the top. Is the logarithm alone? No. So we get the logarithm by itself by undoing the order of operations. And as soon as the logarithm is alone, we go to exponential form. And now we just keep solving for x. All right, solving this equation, I could take the square root of both sides. And when I square root that right side, I get positive and negative e. Okay, continuing to get x by itself, I'm going to subtract over 1. So we have 2 possible solutions, -1 minus e and -1 plus e. All right, when it comes to logarithms, okay, checking your answers is not optional. Recap from this year. If the original equation has an x in the denominator, we're in danger of dividing by 0. If the original equation has an x underneath an even root, we're in danger of getting complex solutions. If we have the logarithm of x in the original equation, if any one of those 3 features is present in the original equation, you have to check your solutions. Okay, because what happens when you go to check your solutions is the answers you think are answers, it may turn out that some of those are extraneous. Fancy word for extra solutions that need to be thrown out. Okay, so as soon as we solve, we're going to substitute them back into the original. I'm going to start by checking -1 minus e. So I'm going to replace the x with -1 minus e. I'm going to simplify the left side to see if it does indeed equal 10. So -1 plus 1 is 0. So all I have left in there is negative e. Now negative e squared, we're not taking the natural log of negative e, we're taking it of negative e squared. So negative e squared is e squared. And you can see I'm being lazy, I'm leaving those parentheses off. Okay, the base on e, or the base, excuse me, on natural log is e. And so we have that property where when the bases match, all of it disappears. So the natural log base e of e to the second power is just the number 2. So 3 times 2 plus 4 does indeed equal 10. 10 equals 10. So -1 minus e is a solution. Next, we want to check -1 plus e. So I'm going to replace the x with -1 plus e. Simplify, -1 and 1, those disappear. And then using that log property, natural log base e of e to the second is just 2. So 3 times 2 plus 4 is 10. So that one is also a solution. Okay, so one more time, recap. we want to get the log by itself by undoing the order of operations. Then you go exponential, and then continue solving to get x by itself. You may want to pause the video and jot those steps down because having the appropriate strategy is going to be key in doing battle with these logarithms. Okay, now I'm going to go through a common mistake that happens because you get so excited about these properties and you want to apply them when you know them. So if I start solving this exact same problem, okay, and then you begin by trying to get one logarithm by itself by undoing the order of operations, I'm going to subtract over 4, that part's good, and then right there you're so tempted to lasso the 2, okay, because you know that property. When a logarithm of something to a power, you think, oh, I'm going to move that 2 to the front. Well, danger, danger. Let's go ahead and do that and see what happens. If you apply the log property by moving the 2 to the front, I end up getting 6. Then I continue undoing the order of operations, so I divide by 6. Okay, and now that I have one log by itself, I go exponential. So the e tunnels under, right, the base e tunnels under, and I have x plus 1 equals e, subtract over 1, and darn it, what just happened is we lost a solution, right? So it's really key. Listen so carefully. Get the logarithm, one log by itself, by undoing the order of operations. No other options. You may only undo the order of operations. Don't apply any log properties when you're getting your log by itself, okay? Because we did get a correct answer, but we lost a solution. Okay, so let's take a look at one more. Here we have our equation, and I selected this one because when we go to see if the log is alone and we begin to undo the order of operations, okay, well, something that happens really frequently with logarithms, mathematicians are notorious for being very lazy writers. And so anytime we can leave something off, we kind of do it. We have the square root of x and we leave off the little index number 2. We're like, oh, that's a super common one. I'll remember it's the second 2 square root of. So in the case of logarithms, you need to understand that when you're taking the logarithm, you know, you're always taking it of something. What you're taking it of is called the argument. And really good notation, the argument should be in parentheses. Now, if you do not see a set of parentheses after the logarithm, I highly recommend that you put in the set of parentheses yourself. Now, you're like, well, does the set of parentheses go around negative 3x plus 1, or does the set of parentheses go around just negative 3x? Well, if the parentheses have been left off, then the only thing that, for lack of a better word, attaches itself to the logarithm is multiplication. As soon as we get to something other than multiplication, that is separate. All right, so negative 3 multiplied by x, those are both multiply, so it's going to attach to the log. But now all of a sudden, plus 1, no, that one is not attaching. So I'm going to insert the set of parentheses there myself. You'll see several problems in textbooks all over the place where they're just lazy and they leave off the set of parentheses. Okay, so when that happens, insert those yourself. Now, if the original problem wanted you to be taking the log base 4 of the quantity negative 3x plus 1, then they'll put in, the only way you can do that is to put in a set of parentheses around negative 3x plus 1. Okay, hopefully enough said, but do make sure the set of parentheses is there before you start getting that log by itself. Now I'm going to go for getting that logarithm by itself. So undo the order of operations to get that log by itself. So I'll subtract over 1. Okay, and then to get rid of multiplying by 1/2, I will divide by 1/2. But dividing by 1/2 means whoop, multiply by 2. So I'm going to multiply both sides by 2. I have gotten the logarithm by itself by undoing the order of operations. Okay, so now we're going to go exponential. All right, so the 4, if we change this to exponential form, the 4 tunnels under like the beaver, and we have 4 to the power of 6. Then that logarithm is gone, and the only thing left over there is negative 3x. So now we just keep on going, getting our x by itself. I might simplify. 4 to the 6th power, okay, is 4,096, and then divide both sides by negative 3 to get negative 4,096 over 3. You can make that an improper fraction if you want to, but I wouldn't make it a decimal because it's going to be a repeating decimal. We're going to just go with an exact value answer. Okay, now don't forget, so easy to forget, if the original equation has an x in the denominator, an x underneath an even root, or you're taking the log of something that has x, you must check the solutions. Okay, so I'm going to grab that original. I'm going to do a better job by putting in the set of parentheses. Okay, I'm going to substitute in negative 4,096 over 3 for x. Doing what's inside, grouping symbols, negative 3 multiplied by negative 4,096 over 3 is positive 4,096. Now, you could grab your calculator right now and take the log base 4 of 4,096 if the calculator you're using will take a base other than base 10. But if the calculator you're using does not take a base other than 10, you'll need to use the change of base formula, which amounts to rewriting this as log of 4,096 divided by the log of 4. That way we have base 10s. So if you grab a calculator, you do log 4,096 divided by the log of 4, and you'll get the answer to log base 4 of 4,096. I went ahead and just threw in an extra property because we might as well practice those. 4,096 is 4 to the power of 6, right? We already knew that way back there. And when those 4s match, when those bases match, all of that goes away. So the answer to log base 4 of 4 to the 6th power is just 6. So all of that is 6. So we have 1/2 times 6 plus 4. And half of 6 is 3 plus 1 is 4. So it turns out that yes, that is our final solution. I know in all the examples that I have shown you today, all of the answers have checked out, but that it will not always be the case. So please, please be sure once you solve an equation that the original, you're taking the log of something of x, you've got to check those solutions. Okay, and then the other quick recap so far about how do you solve an equation with a logarithm? Part 1. We're going to level up next time and we'll have multiple logs in the original equation. Okay, but for now, we only have one log in the equation. So we want to get the one logarithm by itself by only undoing the order of operations. Don't lasso. Hold on there, cowboy. Okay, don't move those exponents to the front. So get your logarithm by itself by undoing PEMDAS, then change to exponential form and continue solving for x. All right, so I love logs and I hope you do too, and I'll see you next time.